Okay, so we're ready to roll. This is going to be the last section we're going to look at in Chapter 5. Multiple angle identities. These are all identities that will be given to you on a sheet later. I'm going to have you write them down today anyways, just so you have them kind of in one place for right now. We're just going to do some of the same things we were doing in the last section with these identities, and that's solving equations using identities, and then also completing some proofs involving these. These are all called multiple angle identities because we have double angle identities, and you'll see why they're called that. We also have half angle identities. Okay, so if I want to take, like the double angle identities, if I want to take a sine of like 2x or something and break it down to be just sine x or something, that breaks those each down. And then the half angle identities is if I have like the sine of x over 2 and I want to turn it into just sine of x or something like that. How do I do that? And then there's also power reducing identities, which like if you have a sine squared and want to bring it down a power, it'll do something like that. So anyways, we're going to start with the double angles. Have you jot these down real quick? All right, so sine 2x is equal to 2 sine x cosine x. Okay, so the double angle is the sine 2x, because it's a double inside there. And then if you want to get rid of the 2x part of it, it's 2 sine x cosine x. Now the cosine double angle, this one's the tricky one. Try to avoid if you can. There's 3 different choices. There are 3 identities for cosine 2x. Yeah, well, it just happens. These are ones where I could go through and show you where they come from. It's starting to get scratchy. But I would rather spend all that time doing it. But the result of working these out, cosine does end up with 3. So that one, no, almost. Pythagorean identity is cosine squared plus sine squared. Yeah. Oh, if you mean by opposite, just like the sign changes in the middle? Yeah, it is. So it's interesting. You put a plus sign here, it's equal to 1. You put a minus sign here, and it's equal to cosine 2x. Who knew, right? This one, 2 cosine squared x minus 1. And this one can be derived directly from this one by taking this sine squared and making it 1 minus cosine squared, and then shifting stuff around. You get this one. And then the third one is also found by doing this one. If you take cosine squared and plug in a 1 minus sine squared and then shuffle stuff around, you get this one.
All the same thing, but shuffled around with Pythagorean identity property.
Yeah, exactly. So you start with this one, and because it's equal to this, you can do those little Pythagorean tricks to get these other 2. It's kind of how it all fits together there. All right, so tangent of 2x, this one, thankfully, there's only 1. It's a fraction, though. Two tangent x over 1 minus tangent squared. Now that one, you're welcome to take the sine 2x and divide it by the cosine 2x, one of those formulas, and do it that way as well. Tangent always has that option, kind of like with the sum and difference identities. You know, we said you could do it with sines and cosines, or you could do it with just tangents. Well, same thing's true here. If you do a sine 2x over cosine 2x, you know, pick one of the cosine 2x ones and divide them, that technically would be true for tangent 2x as well. But if you want an identity for tangent 2x that only involves tangents, then there you go. That one works too. Okay? So those are our double angles. Do the power reducing ones next because they're shorter. All right, so sine squared x is equal to 1 minus cosine 2x divided by 2. Now, take a close look at this right here, and then take a close look down here at this. This is equal to cosine 2x, correct? Right, it's just one of the options, but this is equal to cosine 2x. If I take this equation and solve it for sine squared, it's this. Okay? Why? Because if you have sine squared in your formula somewhere and you need to get rid of it, and you can replace it with this then. So it's kind of the same identity as this one. Okay? It's just by writing it out this way, I think it makes it easier for you guys to use it. So you don't have to think about doing this one and like doing it backwards. Just, I'll just do the power reducing. But it really is technically the same identity, just solved for sine squared. Okay? Just wanted to show you that, just so you know. Cosine squared, it's the same type of a thing. It's using this one. And that one, the only difference is the plus sign. It's 1 plus cosine 2x divided by 2. And then tangent squared. I know it is. It's really annoying. Try turning the volume down just a little bit on both of them. It's a little bit better. Okay, so tangent squared. Remember how I said tangent's always sine over cosine, right? So I can take this and divide by that. See how the 2's would cancel each other out, right? It would be this numerator divided by that numerator. That's it. That's that identity. Those are your reducing identities. The last group we're going to look at are the angle identities. And the angle ones, again, kind of stem from these. Okay, it's thinking about kind of doing these backwards. So they're going to look similar to that. But they get kind of complicated because they involve square roots and that sort of thing. Because when you solve those backwards, you end up having to do square roots. But when you solve something, when you square root both sides, you got to have the plus or minus. And it's the square root of 1 cosine x divided by 2. Done anything with them yet, so hold that. Cosine of x over 2 plus or minus 1 plus cosine x over 2. And then tangent this one. Choices. Yeah. So we've got, just again, taking these two and let's plus or minus 1 minus cosine x divided by 1 plus. The 2's would cancel each other out. That one, choose cosine x over sine x divided by 1 plus cosine. Now, I'm going to be honest. When we get to your quest on Friday, you're not going to see a lot of these. I'm going to try and minimize, there'll be some, but I'm going to try and minimize these as much as I can because they're kind of complicated. And when you're working in a proof, these are not always the nicest ones to work with. But depending on what you're trying to prove, sometimes you do need them. So we're going to take a look and see. But especially these half-angle ones, like I try to kind of avoid those when I can, just because it just kind of makes things overly tedious sometimes. So let's, in general, though, try and use these things, okay? So we're going to solve equations. We're going to complete some proofs that involve some of these. Now, we're also going to have some of those older identities that we've studied popping up as well, okay, as we go here. But we're going to involve at least one of these each time, okay? And sometimes the tricky part's going to be, like for some of those that have more than one choice, which one's going to be the most useful? Sometimes more than one work. Sometimes there's only one of them that work. Be a little bit, well, you got to kind of think forward about where you're headed with it and what might be the best choice then. That doesn't always work. Just hold. The interval 0 to 2. So here's an example where you can't just solve for 2x divided by 2. Because I've got one trig function in there that has a 2x involved with it, and the other one that doesn't. So it's like comparing the oranges at the moment, okay? 2x, and convert it into things that are not double angles anymore, just single x's, then I have a shot at doing this. Or if I take cosine x and convert it into something that involves double angles, so everything has 2 x's in there, then I can do exactly what he was saying. Just solve it for the 2x and then divide by 2 and you get your answer. The easier route is to take the double angle and bring it back, because we're used to working that direction with it, not having to think about what is 2x equal to, but just simply what is x equal to and go that way with it. So we're going to start with an identity on this one then. So the sine 2x identity, okay, what is that? You just wrote down. Equation, I'm doing the same thing, right? I've simply substituted the sine 2x with what its identity says it's equal to, and now I can get started, okay? And you've seen ones kind of like this before that we've solved. So what's kind of the general strategy then? What did we do before? In solving equations. Don't want to divide. We want to do something that starts with the letter F. Yes, we want to factor somehow. What do we need to do first before we can factor it?
What does this one start with?
Yes, yeah. Because we're going to use the zero product property, so we have to have a 0 on one side, right? So when you factor, then you can take your factors, set them equal to 0, and off you go. So what can I factor out of this thing now? Cosine x. We didn't just divide by cosine to begin with. Because if we did that, we would have lost. So we've got cosine x times 2 sine x minus 1 equals 0. So each factor, cosine x and 2 sine x minus 1, could be equal. One, well, basically equals 1 half, right? We add the 1 and divide by 2. So where on your unit circle is sine equals 1 half? Nope. All right, so 6, and there's one other place. 5 pi over 6. And there we solved that equation then. Okay. We had to go through that identity to get there, though. There's no other way to do it. So sine squared x equals 2 sine squared x over 2. Here, we might, as an identity, we might need to use. Not all. Or 2 don't match. We're going to have to resolve one of them. Okay. So this x over 2, if we change that to an x somehow, we can do that. So all right, so if we apply that angle identity, the angle identity for sine, what's the square root of 1 minus cosine x all over 2? One. So what's going to happen then? Yes. And even the minus goes away. Why does the plus or minus go away? Right. Whether it's positive or negative, when you square it, you'll get the same thing. Okay? So that all goes away. So 1 minus cosine x. And then we got a simple little cancellation with the 2's there. So,
Cosine squared, so you have cosine x equals cosine squared x.
I hear you. Okay. So add the cosine over here, so we have cosine x. And then subtract the sine squared over to the side, so we have 1 minus sine squared.
Yeah.
So, all right. So everybody, are we cool? Following them so far? I like this. This is good. Okay. So, and then you said 1 minus sine squared is cosine squared, right? Okay.
And then
Squared x minus cosine x. 0. Because now we got something to factor, right? Pull out a cosine, like you said. So equals 0. Okay, so we got 2 to solve here. Cosine x equals 0, and cosine x minus 1 equals 0. So, you already answered it up here. Where is the cosine equal to 0? One, 0, and those 2 there. So we got 4 solutions there then. 2, 3 pi over 2, 0, and 2 pi. Okay, so it's doable, but again, have to go through to get rid of this. You know, if these are, like I said, if these are not the same, we got to resolve that somehow. We're able to do that, and then from there, we have to be able to factor the thing too. So you might have to pull in another identity. In this case, it was a Pythagorean identity to get us to a point where we were able to factor what we had, and then solve it from there. Okay, so that's some proof work with it here. This one may not be. It's not a 20. Okay. So with this one, what side of the equation? Doing the Pythagorean identity 2 times, unfortunately. Kind of nice. Ed, we can use a Pythagorean identity here. If you take a look, we have a difference of squares here. Even though it's to the 4th power, you can still factor that, right? Okay. Everybody see how I did that? Because they're to the 4th, I'd have to make what's in the factors to the 2nd. But cosine squared minus sine squared times cosine squared plus sine squared. Safe. Yeah, it's factoring using difference of squares, if you want to get real technical. What? Yes.
cosine.
And so somehow we need to take cosine squared minus sine squared and get it to cosine 2 theta. Yes.
That is equal to
Because of the double angle identities, right? Your double angle identities, do you see cosine 2 theta or cosine 2x? Sine squared is one of the three that's in there, right? So yeah, what's your double angle identity for cosine? See how one of the three of them, I think it's the first one we wrote down, was cosine squared minus sine squared. So we're just going backwards with that. We can still use that identity that way. It's fine. Okay. So, and that'll be it. Here. Okay. Yeah, 4 steps there. Okay. So. A proof, but I think it's good to do because some of the proofs you're going to see in your assignment. So we're going to prove that. Yes. Because here's the deal. When you have ones like this, yeah, normally complicated side and then simplify it down. When you're dealing with anything power reducing, which obviously we're going to have to power reduce this thing down to get it to where we want it to be, you want to start with the higher power of it. Okay? So cosine to the 4th x is our starting point then. Look at power reducing identities. Do any of them have a 4? What are all of them? 2's. So is there a way I could rewrite cosine to the 4th with 2's to make it so I could actually use one of those? Thank you for raising your hand.
Did you have 1 plus cosine over 2 squared, like squared?
Nope. Think simpler than that. Something to the 4th power. Right. Yeah. That. Okay? So cosine squared, same thing. What do you suppose? It's factoring. Yep. Yeah. Anyway, we have, quiet. We have a reducing identity for cosine squared that we can just dump into there. Okay, so we're to there now. Multiply the thing out. Okay. Do all my foiling and all that kind of business. 1 plus 2 cosine 2x plus cosine squared 2x all over. So, getting there. See how we have a cosine 4x in there? Sort of like that. But there's still this cosine squared where we're at, and we're trying to reduce that one down so we can make it a reducing identity again. Then we can do that. Okay? We just need to power reduce this right here. Okay? Because it needs to be essentially looking like this. And so we got to power reduce this cosine squared and then shuffle things around, simplify, simplify, simplify as much as we can, and hopefully get it to look like this. So that's going to be where we're headed next here. So
You multiplied that by
you end up and then away. Yeah, you could do that right now, or you could wait till the end. At the end, it'd be about the same work either way. But yeah, wait, that's fine. Here, so hold on just a second, because yeah, so the cosine identity for cosine squared of a single x is this 2x. So what you do to whatever's in here, you double it. You multiply it by 2. So if you have a 2 reducing, it becomes a 4x. You just multiply it by 2. Same kind of thing. And with a 2x in there, it's going to make it a 4x then. And now it's just a matter of multiplying things together, simplifying. All right, and now if I pull out a 1/8, what I two terms. If I take a 1/8, 1/4, 2, right? An eighth is a fourth, so I'd have to leave a 2. What would be left over from the 1/2? 4. Here, do you see how this is just moving out, and then it's just the 1 plus cosine 4x left over? Two plus 1 is 3, right? So, yeah, those aren't the most fun ones to do. But it is doable, though. Okay? Can't get through it, but it's a lot, your hand cramps up or whatever. It's a lot of writing and sort of thing. But some of those power reducings, if they get powers above 2, then they start to get a little involved. But, yeah. Enough for you guys to get going on your homework, so I'll there.